So in this lecture, we'll talk about embedded systems and how they are related to IoT devices. There's a lot of overlap. Embedded systems, the term usually refers to a lot to not just how the device is used, but also how it's implemented, how it's built. So there's a lot of overlap between the two terms, and IoT devices are typically embedded systems also. So we'll just define that and give you an idea of what embedded systems are. It's good to know the term embedded system because it's still commonly used, and what we're building are typically embedded systems. What we'll talk about building later in the class, they're actually usually embedded systems. So what are embedded systems? Embedded systems are systems, they're computer-based systems that don't look like computers. Okay, that's my simple definition. The complexity of a computer is hidden from the user. So if you have a computer, desktop, laptop, something like that, if you've ever used it, which I know you have, there are complexities to using a computer. So say you want to install some new software, right? You install software, sometimes it's easy, but sometimes there's a conflict. Like, for instance, video games. I used to play video games on computers. Now I use only game machines, but say I play a video game on a computer. I put the video game in there, install it, and it has some conflict with the video card. I need a new video card, right, to play this new video game. So then I need to get new drivers for my video card. So there's this interaction, right? The functions are not separated. Right? This is different than an IoT device. Or an IoT device, it basically has one function. We talked about this last module, right? It has one function it's trying to do, like a car. It does car things, right? A camera does camera things. But a general purpose computer, it can do a lot of things. And so there can be conflicts. So if I install software to play a video game, that might interfere with the software to do something else. So these relationships add to complexity, right? And so it makes it harder to use a standard computer than it is to use, say, an IoT device. Now, an embedded system, and IoT devices are generally embedded, they hide the complexity from the user. So the picture we got here, this is some kind of a scale, let's say. And say it's an IoT scale. So the user doesn't have to see the complexity of what's going on inside. The user just knows how to use it. So it has a very simple interface. And and this is where the term embedded comes from. The complexity is embedded inside the device. So the user doesn't have to deal with the complexity. So that's what an embedded system is, how the term came about. Now, these embedded systems are much more common than desktops or laptops because there is computational ability built into a lot of different devices. Now, one thing to notice about embedded systems that's necessarily different, not necessarily, but can be different than IoT devices. IoT devices are almost always connected to the internet, thus the term Internet of Things. Embedded systems may or may not be. Embedded systems may have computational complexity in there, but no network connection at all. And so there are a lot of uses for devices like that. Things are moving from embedded to IoT because of the trends we talked about in the last module, the fact that internet connectivity is so ubiquitous and it's pretty cheap to attain. So a lot of these devices that used to be just embedded are now becoming networked, and so you would call them IoT. So what are embedded systems? They're basically everything that interacts, all the Internet of Things devices that we talked about, but plus or minus the internet part. So take a digital camera. That's what we have here. Digital camera, it's a basic digital camera might not be networked, right? It might just be an embedded system where you press a button, you take a picture, and the picture is stored locally, but it might not be immediately networked, right? So you would call that type of thing an embedded system because the complexity is embedded within the device. So a camera, an old camera, totally mechanical camera, has the same interface. You press a button, it takes a picture, right? New digital camera, same interface. Press a button, takes a picture, but there's a lot more complexity to what's going on inside. So that's the term embedded, right? The complexity is embedded inside the device, and the user doesn't have to see it. The user can benefit from the complexity, but using a very simple interface. Now, sometimes embedded systems don't interact directly with the user, but they interact with the user through another device. So what do I mean by this? Let's take this thumb drive, right? Now, thumb drive, you've seen this type of thumb drive. It stores data. This type of thing does not interact directly with a user, right? A human doesn't connect this up to their body or something yet. Right now, they connect it to their computer, something like that, or their phone, or whatever it is, and then they interact with it. They can access the files on it through another device. So you would also call this an embedded system, even though it's not directly interacting with the human. And you see this in other devices like a car, the anti-lock braking system inside a car. That's interacting with a human, but not directly, right? The human presses the brake pedal, and the brake pedal talks to the anti-lock braking system. So the human interacts with the car, and the car talks to its subsystem. One big property of embedded systems and a difference in embedded system design is that efficiency is really important. So what that generally means is that it's not enough to get the design to work, to do its task. It has to do its task in an elegant, let's say an elegant way, okay? Either it has to do it fast, or it has to do it with low power, or it has to do it with at low price, right? So it's not enough just to get it to work. And this is actually a big difference between embedded system design and, say, traditional software design. So I teach programming too. When we teach programming, generally we just teach how you get something to work. Here, your goal is to get this code to do what it's supposed to do, whatever I want to do. Sort this list of items or something like that, right? But I'm not usually saying in that class, it has to sort this list of items and it has to use the minimum amount of memory possible. I'm not saying it has to sort these items and it has to do it within 1 second, right? I don't put these constraints on it. I just say get it to work. But with embedded system design, you care a lot about the efficiency. You can't just get it to work, it's got to do it in an efficient manner. So what that means is that, the reason for these constraints is that most of these devices are used in cost-critical markets or in life-critical, right? So if it's used in medical or military, people's lives depend on these devices. And if it's used in cost-critical devices like consumer electronics, the cost is important. But either way, there are some constraints that are important to you. Besides just getting things to work, it's got to work within a tight set of constraints. So, for instance, say it's a consumer device, like a phone. So manufacturing costs and design costs and time to market, those things are primary. Because you want it to be cheap, right? You want to make money off the device, so the cost has to be low. Also time to market, because you have competitors. And this competitor's coming out with a new phone on this date, so you have to come out on the same date with a phone that's better than them, let's say. So those things are primary. But if, on the other hand, this is the military, this is going into a tank or a weapon system, and people's lives depend on it and it's life critical, then you care about performance and power more. So if you're in the military, you might say, look, we'll pay millions of dollars for this device as long as it works and it can effectively do what we need it to do. Right? So cost becomes less important, but power and performance really matter. And same thing with medical, right? You might be a lot more willing to pay a lot of money for a device, but it better work and it better maintain your heart the way it's supposed to, like a pacemaker. That thing better have high reliability, and it better control the pace of your heart properly. So if that means costing more money, then so be it. So in these embedded devices, there's always this tight set of constraints that you're working under. So it's not enough to get it to work. You got to get it to work within the set of constraints that you're given. So this is very different than traditional software engineering, where you just want to get it to work and get to work somehow. And the assumption there is that Moore's law will save you eventually. So by Moore's law, you may have heard of this before, but Moore's law just says that, let's say approximately says that machines get faster and more computationally efficient every year. Right? They get more dense and faster, which, by the way, Moore's law is slowing down, but still, this happens. Machines improve. So software engineering, often you'll just say, look, just get it to work, and if it's slow, it's okay, because processor performance is improving every year, and so in the future, it won't matter. Right? So that was the background assumption to a lot of software engineering. But embedded systems you can't think like that. You have to think, look, not only does it work, it's got to be working fast, it's got to be working low power, and all this. Thank you.